Okay, so let's get started with chapter 10, which is the quantum mechanical model of the atom. So let's start off with understanding a critical set of properties of light. So light can be modeled and viewed in one perspective as a wave. So just like, for example, a wave traveling through the water when you're at the beach. A wave has the following characteristics. First, it has an amplitude that we call A. Okay. The amplitude represents the magnitude of the wave at any given point. The wavelength is the distance between the maximum amplitude of a wave, or the distance between any 2 points on a wave of the same amplitude. Okay, so wavelength is formally defined as the distance that light travels to complete one cycle, and the units are typically in nanometers. So this wave is not stationary for a light wave, it is moving through space with a velocity. Okay, and the distance between the 2 points of maximum amplitude is known as the wavelength. The frequency is the number of wave cycles in 1 second. So for example, if in 1 second the wave travels the following distance, we then can count the total number of wave cycles that occur in 1 second. So a complete wave cycle has a region of positive and negative amplitude. So this is one wave cycle, and we have a second wave cycle. So frequency tells us the number of wave cycles that occur in 1 second of time. So for example, this top wave here would have a frequency of 2 cycles per second. Okay, so these are the characteristics associated with waves, and specifically light waves. Now, in connecting this to some real world phenomena that we can observe, the wavelength of light is indicative of its color, whereas the amplitude is indicative of the brightness or the intensity of the light. So depending on the wavelength, we either have light in the non-visible, visible, and infrared or radio wavelength range. So in general, a small wavelength implies we have high energy light waves. So these are known as typically ionizing radiation. So when they impact objects and chemical materials, they can impart energy and lead to ionization and other detrimental processes. While if we have a large wavelength, we generally have low energy waves. Okay. So the visible range, the range of wavelengths of light that we can actually observe, range from about 400 to 700 nanometers. So the visible range is 400 to 700 nanometers. Okay, so we've looked at some basic properties of light, and we've connected it to this idea of color and whether or not we can see the light waves with our eyes, or see the light's color and characteristics with our eyes. Now, the speed of light in a vacuum, which is known as the constant c, relates the wavelength of light, which is known as lambda, to the frequency that we call V. So the frequency of a light wave is equal to the speed of light, which is 2.998 times 10 to the 8th meters a second, over the wavelength. Now for your wavelength, you're going to need to make sure to convert to meters. So this is really important. Now, a side note, in this equation, one really fundamental property of light that needs to be discussed is that regardless of the frequency, light travels at the same speed c. Okay, so let's show how we can use this equation to relate the frequency and wavelength of light. So for example, if a light wave has a frequency of 4.68 times 10 to the 14th second inverse, we're asked, what is the wavelength? Well, we know that frequency is equal to the speed of light over the wavelength. So then, rearranging this equation, the wavelength is equal to the speed of light over the frequency, which gives us 3 times 10 to the 8th meter per second, divided by 4.68 times 10 to the 14th, 1 over seconds. So punching this into our calculator, so we have 3 over 4.68. That in turn gives us 6.4 times 10 to the negative 7th meters. And just to convert this to nanometers, 6.4 times 10 to the negative 7th meter. We know in 1 nanometer, we have 10 to the negative 9th meter. So this turns into 640 nanometer. And if we look at our range, this light is likely to be in the red wavelength range. Okay, so this is how, given the frequency for a light wave, we can solve for the wavelength and in turn predict the color. Any questions on this example?
Where did you get the 3 times 10 to the 8th?
Yeah, I rounded the speed of light, so if you,
Okay.
but I can punch that in as its full number.
Oh, okay. I get that. I know it's like 2.998, so.
Yeah, it's often sometimes presented in other texts as just 3 times 10 to the 8th to make it a little bit easier to enter into your calculator. But whatever value you're given for this constant, that's what you should use in the calculations, for example, on Canvas.
Okay, thank you.
So now that we've seen an example where we've related the wavelength and frequency of a light wave, let's try to calculate the wavelength of a radio wave, where given the frequency is 300 megahertz, where the mega prefix, so for example, a megahertz is equal to, what power of 10 is this mega prefix? Would someone like to share that in the chat? What power of 10 is the mega metric prefix? 10 to the 6th, exactly right. So given this information, let's take about 3 minutes and let's try to calculate the wavelength of a radio wave in meters. And if you have any questions, don't hesitate to ask verbally or in the chat. And looking at the setup provided, the setup I see in the chat looks good, except remember that mega is 10 to the positive 6. So your power of 10 should be positive 6 instead of negative 6. Otherwise, the setup looks good. Let's spend about another 1 to 2 minutes on this example, and then we'll discuss. Okay, so again, just to demonstrate the fact that radio waves have a relatively large wavelength and are relatively low in energy, let's now calculate the wavelength of a radio wave. So wavelength is equal to the speed of light over the frequency. So we have 2.998 times 10 to the 8th meters per second over 300 times 10 to the 6th seconds inverse, which I write as 1 over seconds. Seconds cancel. And punching this into our calculator, we have 9.99 times 10 to the negative first meters that we round to 1.00 meters. Okay, any questions on this example? So in effect, we've looked at light waves, we've characterized their frequency, their wavelength, and now what we're going to do is we're going to talk a little bit about light from not only a wave perspective, but another perspective introduced in quantum mechanics is this idea. Sorry, what was the question in the chat? Oh, 1 over second, because a second inverse can be thought of as 1 over seconds. Does that make sense? So a hertz is a second inverse, which is 1 over seconds. And I just write it that way so I can cancel the units. So now what we're going to do is we're going to look at light and try to understand the energy associated with a light wave. And then we'll also be introduced to another view of light, which is light as a photon or a particle with discrete energy. So we're next going to look at the concept known as the photoelectric effect. Curiously enough, this was actually the experiment and work that was the basis for Einstein's Nobel Prize. It wasn't actually for relativity, which was considered controversial at the time, but for the photoelectric effect, which is a really beautiful experiment. Okay, so here's how it works. So shining light on a metal surface where your light is above a specific frequency results in the emission of an electron. I'm not sure for the full reasoning behind why the idea of relativity was, it was quite an interesting and new way of looking at the world. So sometimes it's hard to understand why the Nobel Committee chooses to focus on certain experiments over others, but this experiment certainly really helped open the door and really provide some wonderful evidence supporting a particle view of light. So when we shine our light on a metal surface above a certain frequency, we observe the emission of an electron. We can see the electron visibly spark off of our metal surface. Now, what's going on in this process following conservation of energy is that we have transfer of energy from the light to the metal, and that results in the emission of an electron with kinetic energy. Now we can measure the kinetic energy of the electron by adjusting the electric field strength until the electron can no longer move against the electric field and reach the detector. Okay, so we shine our light on our metal sample. We keep tuning our electric field, and if we observe a signal, we keep adjusting until the signal disappears. Now, why is this experiment so interesting? Well, we can measure directly the kinetic energy associated with our emitted electron. And we can measure that electron energy for different light intensities and frequencies. And our question that we're going to try to answer is, what properties of light determine the energy of a light wave, and I'm going to put also in parentheses, or particle. So what properties of light are relevant to determining the energy of that light wave? Well, classical physics predicted that the intensity of the light, the brightness of the light that you're shining on your metal, affects the kinetic energy of your emitted electron. Well, looking at the results from this experiment, we have the rate of electron ejection as a function of the frequency of light. And we have two trials, one for a high light intensity and the second for a low light intensity. And now my question to all of you is, looking at this chart, what seems a little bit odd? What seems a little bit odd? So if the electron emission is thought to only depend on the intensity of the light that is projected onto our metal sample, what is odd about this chart? Do we see something odd in this chart? Or to help guide us along, do we see any electrons emitted below a certain frequency? Do you notice how this graph just cuts off below a certain frequency? So then my question to all of you is, does the electron energy depend more on the intensity of light or the frequency of light? Where do we see a greater dependence? On intensity of the light or frequency? And don't be shy to submit your response in the chat. Frequency, exactly right. And we see this really dramatic effect. This was quite shocking at the time. The intensity of light only affects the rate of electron emission above a threshold frequency. So this frequency value is known as our threshold frequency. And below your threshold frequency, so below your threshold frequency, we see no emission of electrons. No matter how we adjust the intensity of the light that we use. This strongly suggests that the energy associated with light is heavily dependent on the frequency rather than on just the intensity. So metals are experimentally found to have a threshold frequency below which no electron emission was observed. The intensity of light did not affect the emission of the electrons or the kinetic energy of the emitted electrons. Instead, the kinetic energy of the emitted electron and the frequency of light was found experimentally to follow the following relationship. Okay, where this constant here is known as the binding energy, and this constant H, which is a constant we'll be seeing a lot in this chapter, is known as Planck's constant. So, the really key feature that I want you to know and be familiar is that the energy associated with light is dependent on frequency rather than just intensity. So looking at the photoelectric effect, we could determine this constant H experimentally by plotting kinetic energy as a function of frequency. And it was found that Planck's constant is equal to 6.626 times 10 to the negative 34th joule seconds. Additionally, from this plot, we can also determine our binding energy as well as our threshold frequency. Okay, so just to walk us through how this graph is generated, we know that by conservation of energy, any energy gained by the electron came from our absorbed light. And as we see experimentally, the energy associated with the light is dependent on the frequency of our light that we've projected onto our metal sample. Now, this dependence and this representation of the energy associated with our light as HV provides an idea and provides us a very interesting perspective into the nature of light. So rather than just viewing light as a wave with energy proportional to its intensity, in this perspective, we can instead think of light as a collection of particles, each with discrete, defined, quantized energy proportional to the frequency of light. And we call these light particles a photon. So the photoelectric effect showed that the energy of light is quantized. It exists rather than as a continuous range of energies. Light can best be thought of as packets or quanta of light with energy proportional to frequency. So we can think of light as like a collection of tiny little packets, tiny little particles called photons, each with an energy equal to Planck's constant times the frequency of light. Okay, so rather than just thinking of light solely as a wave, we can also view light as a collection or essentially a collection of particles called photons, each with distinct energy. So just like before, we can calculate the energy associated with a photon by taking Planck's constant times the speed of light over the wavelength. Note that this equation is calculating the energy of a single photon. If we wanted to calculate the energy of 1 mole of photons, so the energy of 1 mole of photons is equal to the energy of a single photon times Avogadro's number, which is 6.02 times 10 to the 23rd photons per mole. Okay. So we can look at light as a collection of light particles known as photons. So let's show how we can put this into practice. So first, let's try to answer the question, is ultraviolet light higher energy than red light? Well, we'll just calculate the energy of each of these 2 light samples. So first, we can calculate the energy associated with ultraviolet light, which is equal to hc over lambda. So we have 6.626 times 10 to the negative 34th joule second times 2.998 times 10 to the 8th meter per second over our wavelength, which is 320 nanometers. And now this is a critical mistake that often I see made in this chapter. Do my units cancel as written? Do my units cancel as written? Do the units cancel as written? Yes or no? No, they don't. So let's convert nanometers into meters. Oops, that's the wrong way. We know that we have 10 to the negative 9th meter per nanometer. Nanometers cancel, meters cancel, seconds cancel. We're left with an energy in terms of joules. Okay, perfect. So now we're set up and ready to go to punch things into our calculator. And that in turn gives us 6.2 times 10 to the negative 15th joules. Okay. Let's look at the energy of our red light sample, which would be equal to hc over lambda once again. So we have 6.626 times 10 to the negative 34th joule second times 2.998 times 10 to the 8th meters per second divided by 320 nanometer times 10 to the negative 9th meter per nanometer. The 6.626 is known as Planck's constant. And Planck's constant is given up here that we found experimentally to be 6.626 times 10 to the negative 34th. Did that address your question? Perfect. So now that we have this equation set up and our units cancel, all we have to do is execute. Except this time we're plugging in the wavelength for our red light sample, which is 700. And that in turn gives us an energy of 2.8 times 10 to the negative 15th joules. Now comparing the energy of our 2 light samples, the first is at 320 nanometers, and the second sample is at 700 nanometers. We clearly see that ultraviolet light is higher in energy. That's why the saying that ultraviolet radiation is damaging to the skin, well, because it's higher energy light. And as a result, it's more readily able to affect ionization and initiate reactions in molecules. Does this example make sense? How we calculated the energy of different light samples based on the wavelength? If we don't have any questions on this example, let's try to calculate, and let's take a few moments to calculate the energy associated with a photon of light with a wavelength of 450 nanometers. So I'd like you to calculate the energy of a single photon with wavelength 450 nanometers. And then I'd also like you to take this one step further, and I'd like you to calculate the energy of 1 mole of photons with the wavelength equal to 450 nanometers. So let's try to work on this question. We'll spend about 3 to 4 minutes on this question, and then we'll discuss momentarily. Yes, the statement in the chat looks exactly right. And we've actually seen this in practice in our example when we looked at radio waves versus ultraviolet radiation. Exactly right. The shorter your wavelength, the higher energy your light will be. The longer your wavelength, the lower the energy. Yep, exactly right. So let's keep working on this example, and don't be shy to submit your proposed responses for the energy of a photon and the energy of a mole of photons, and we'll discuss this example in about 2 minutes. Let's try to get a few responses in the chat for the energy associated with a photon, and then we'll discuss this example in about another minute to a minute and a half. And let's now discuss this example. So first, we know that the energy of a photon is proportional to the wavelength through the formula hc over lambda. So plugging in our Planck's constant is 6.626 times 10 to the negative 34th joule second. The speed of light is 2.998 times 10 to the 8th meter per second. And our wavelength is 450 nanometer. And we know that there are 10 to the negative 9th meter per nanometer. So punching that into our calculator, 6.626 times 2.998 over 450. That in turn gives us an energy of 7.3 times 10 Let me check one moment. 10 to the negative 15th joule seconds. Okay, if we wanted to calculate the energy of 1 mole of photons, if our energy is 6.3, oh, not joule seconds, just joules, 7.3 times 10 to the negative 15th joule per 1 photon. How do we calculate the energy associated with a mole of photons? How many photons are in a mole? How many photons are in a mole? What number do we use to count a large number of photons? What number do we use to count a large number of things or a mole of things? What number springs to mind when we talk about moles? If we were converting, for example, from atoms to moles, what number would we use? If we're converting from atoms to moles, what number would we use? Avogadro's number, exactly right. And we know that we have 6.02 times 10 to the 23rd photons per 1 mole of photons. And that in turn gives us 4.4 times 10 to the 9th joules. And this is the joules per mole of photons. Any questions on this example? If not, let's keep going now, and let's look at atomic structure, and let's review our current most updated model of the atom from previous chapters before we expand on this model and we start to look at other models of atomic structure. So the first model is the Rutherford model, which proposed most of the atom's mass and all of its positive charge are contained in the nucleus, shown here. The majority of the volume of an atom is empty space, okay? And atoms are neutral, and there are an equal number of negatively charged electrons surrounding the nucleus and positively charged protons in the nucleus. Now, it may just be me, but when you hear the phrase electrons surrounding the nucleus, that to me seems a little bit ambiguous. Well, where are the electrons exactly? Where are the electrons constrained to be located? Okay, so here are some key issues. So what values of electron energy are allowed? Why are atoms stable? So we have this positive charge, we have this negative charge, and intuitively, we would expect that these opposite charges attract. So then the question becomes, why are atoms stable? Why do atoms not just spontaneously collapse as the electrons are attracted to the nucleus? Obviously, since we're talking and we're discussing this idea, atoms clearly are stable and they clearly don't just collapse. So let's try to investigate why are atoms stable. Let's try to develop a working model that accounts for atoms' clear stability. Now, a second major issue with this model is that if electrons are surrounding the nucleus, why do they not spiral into the nucleus? Again, similar idea. We have a positively charged nucleus. We have a negatively charged electron. And why does the electron not just spiral into the nucleus? Why is the electron not just immediately attracted and collapsing into the nucleus? The Rutherford model doesn't account for any of these clear issues. So let's now look at some experiments that were performed and some phenomena that we can observe that can help us revise our atomic model. Okay, so atomic emission spectra. So elements exhibit characteristic colors when burned. So for example, in signal flares, which have a distinct red color, that could be typically strontium. So depending on the exact element, we each observe a unique flame color. Further, when gaseous elements are excited with an electric current, a characteristic color is observed. So if anyone's ever seen a neon light, you have observed an emission and light emission from a sample of neon gas. And that's obtained by exciting your neon gas with an electric current. So whether exciting with a flame or an electric current, we are putting energy into our sample, and in turn, our element sample releases light. Now, this is a really important phenomenon since it helps us understand something really critical about electron energy. So let's answer the question first. Well, how is light emitted from a sample? So you can think of it as a step-by-step process. So first, an electron gains energy and moves to an excited state. Okay? So initially, we're low energy. We gain energy from either heat or an electric current, and we move to an excited state. Okay? Now, inevitably, the sample will return to the ground state, will relax back down to its lower energy state, and as a result, when your electron loses energy, when your atom loses energy as your electron drops back down to the lower energy state, by conservation of energy, this difference in energy is released as a photon with E equals hv. So then, the energy associated with our photon directly depends on the difference in energy between our initial and our excited state. Additionally, we also know that the energy of an electron can depend on the distance of an electron from the nucleus. Okay, so then, just to break this down into a step-by-step process. First, the electron really wants to be close to the nucleus. Electrons are stabilized by the nucleus. Energy is then added to the atom in the form of an electric current or heat, and the electron moves to an excited state. In the excited state, the electron is farther from the nucleus. And it's higher energy. Okay, now inevitably, that electron is going to return to the ground state. It's going to return to its lower energy state. And now there's a clear difference in energy. There's a clear difference in energy between the excited and the ground state. And as the result of conservation of energy, that energy that the atom loses as the electron drops back down is released as a photon. And the energy of our photon is equal to the change in energy of our atom. This is based on conservation. So then we can directly relate the change in energy of our atom to the energy of our photon, and as a result, the wavelength of our photon. Now, the key thing I want you to take away from this whole overview is that since the energy of an electron depends on its distance from the nucleus and its position relative to the nucleus, if electrons can occupy a continuous range of energies and distances or positions, we would expect to see a continuous range of light wavelengths emitted. We would expect to see a range of colors emitted, and we would expect it to be a continuous wavelength range. Okay? Now, with our predictions in mind, so with our current predictions from the Rutherford model, let's compare what we observe in reality. So again, from our Rutherford model, we're thinking right now that if electrons can occupy a continuous range of energies and distances, we should see a continuous range of light wavelengths emitted. Well, if we take our sample and we use a prism to separate the light into its component wavelengths, we can actually observe the spectrum for different elements. We can observe the emission spectrum for different pure elements. And for hydrogen, as we can see in this figure here, whoops, one moment, as we can see in this figure here, let me draw out the emission spectrum for hydrogen. So we have wavelength, and we will observe a series of wavelengths for hydrogen. And one thing that immediately stands out, at least to me, when I look at this emission spectrum for hydrogen, and I'd just like you to answer this question: do we observe a continuous spectrum for hydrogen? Do we see just a consistent block of every wavelength range, or do we only see specific wavelengths? Do we see a continuous block of every different wavelength, or do we only see specific wavelengths? So a continuous spectrum, we'd expect to see almost like a rainbow, where we have all the wavelengths from the lowest visible range to the highest visible range. Instead, what we observe and what we see in this figure is what? Do we observe a continuous spectrum or a discrete spectra? Do we see blocks of wavelengths, or do we just see individual wavelengths? Discrete, exactly. We observe what's known as a line emission spectra for hydrogen and other elements. And what this is telling us is that only discrete, only certain specific wavelengths of light are emitted. So we don't see every wavelength in the possible visible range. We only see exact, very specific wavelengths for each element. And that's what gives each element a unique color for its emission spectra. Now, why is this important? Why are these 4 lines so very important? Well, if we apply some logic to this, we can actually begin to understand something really important about electron energies from this picture. So we know that the wavelength of light emitted is based on the change in energy between the electron's initial and final energy. So if we have initial and final, the wavelength of light emitted is based on the change in energy, which we call delta E. So delta E atom is equal to negative E photon, which is equal to hc over lambda. So then we can relate our wavelength of light emitted to the change in energy for our atom. Now, what's really cool is that because we observed a set of discrete wavelengths for atomic emission, we know that because the wavelength, only certain wavelength values are allowed, only certain energy values are allowed. In other words, the change in electron energy must be a discrete defined value specific for each atom. Thus, and this is really important, this is our payoff, electrons in an atom have discrete energies. The electrons in an atom can only have specific defined energies. In other words, we say that the energy of an electron is quantized. It's divided into discrete energies or discrete steps. Does this idea make sense to everyone so far? This last sentence is our payoff here. This is what I want everyone to take away from this discussion. The electron energy is quantized. We can only have specific electron energies and specific electron positions relative to the nucleus, at least under our current model, which we're slowly developing to the Bohr model of the atom. Any questions so far? Does this make sense so far? Don't be shy to type any questions or concerns or comments in the chat. I know that for quantum, it's very concept heavy. So I'm trying to distill it down to the key takeaways that I want you to remember, because we're going to be using these ideas later on to start to describe reactivity, energy, etc. Okay. So, as we've already discussed, electrons are stabilized by the nucleus, so electron energy increases with distance from the nucleus. So the key thing that I want you to take away once again, electrons occupy discrete energies and distances from the nucleus. Now, how can we use that? Well, in the Bohr model of the atom, which is our next most recent model in chemical history, the Bohr model has the following postulates or ideas. Electrons occupy distinct energy levels indicated by the quantum number n. Electrons also have discrete energies based on their energy level and position relative to the nucleus. Electrons in each energy level orbit the nucleus at fixed distances from the nucleus, and orbit positions labeled with the integer n have a specific energy. Now we've heard this value n mentioned a lot. What is n? N is defined as the principal quantum number, which indicates electron energy and distance from the nucleus. So the larger our value of n, the larger our energy and the farther we're away from the nucleus. Now, the Bohr model, unfortunately, has a few stopgaps just to keep things from immediately going south. The Bohr model proposes that electrons do not emit radiation as they accelerate, as they rotate and orbit the nucleus. And the other major postulate is that electrons will gain or lose energy when they move from one orbit to another. So the Bohr model, if you've ever seen planets in a constellation kit, so we'd have our nucleus and then we have our electrons orbiting our nucleus at fixed distances, almost like planets orbiting the sun. The key thing and the key takeaway from the Bohr model is that the distance and the energy of an electron is fixed and depends on your quantum number. The energy is proportional to the quantum number n. Does this model make sense to everyone so far? Can everyone somewhat visualize the Bohr model, how it's representing our nucleus and how it positions our electrons? Does the Bohr model make sense so far to everyone? So this is the second most updated atomic model, and the Bohr model gets a lot of things reasonably right, but it has some major flaws. And what we're going to do now is we're going to take the Bohr model, we're going to look at a few more experiments and a few more ideas, and we're going to revise this Bohr model and modify our model of atomic structure to attempt to fully explain electron energy, atomic energy, and eventually reactivity. Any questions so far? Okay, so let's take a look at the Bohr model and let's try to use the Bohr model to begin to explain emission spectra and electron energy. So electrons and atoms are found in these principal energy levels denoted by the symbol N. Each principal energy level, or shell, has a discrete energy and a discrete distance from the nucleus. The principal energy level N is actually directly tied to the periodic table in that the principal quantum number N for a given element for the outermost electrons is equal to the period number. So for example, if you were to look at the periodic table, and this is pretty cool, if we look at hydrogen, which is in the first row of the periodic table, so hydrogen would have an outermost N value equal to 1. Okay. And this will be important because we can use the principal energy level to begin to describe the energy of electrons in atoms such as hydrogen. Okay, so let's keep going. Electrons closer to the nucleus are lower in energy as they're stabilized by the nucleus. And it was found experimentally by studying the emission spectra of hydrogen that the energy of an electron in hydrogen was found to be 2.18 times 10 to the negative 18th joules over N squared. And this energy is negative to reflect the fact that the electron is stabilized by the nucleus. And this is a stabilizing interaction. So electrons want to be associated with the nucleus, and they want to be as close as possible to the nucleus. So again, this n value is known as the shell number or the principal quantum number. Now you may ask, how was this relationship derived? Well, by studying the emission spectra of a hydrogen atom, we can in turn calculate the energy or the change in energy of an atom when an electron transitions between energy levels for hydrogen. So we now have an equation that looks at the change in energy for a hydrogen atom as a function of the initial and final quantum number or shell number for that electron. Now, because energy is conserved, the energy of the photon absorbed or emitted during this process is directly related to the change in energy of our atom. In other words, the energy associated with our photon is equal to -1 times the change in energy of our atom. And that gives us hc over lambda is equal to the following expression for our atom's change in energy. So then, and this is really cool, by measuring the wavelength for each emission in hydrogen, we can calculate delta E for each transition. So measuring something really simple, just the wavelength of light emitted from a hydrogen atom, that we can do using relatively simple technology. This is actually done as a teaching lab in person. We can in turn begin to understand and calculate the energy of an electron as a function of principal quantum number. Really powerful stuff. Okay. Now, there was also, outside of the Bohr model for emission spectra, there was also an empirical model. And this was obtained via brute force experimentation and collection of data and generation of a trend and relationship between the wavelength of light emitted and the principal quantum number or shell number n. So for hydrogen, the empirical model for the hydrogen emission spectra is known as the Balmer-Rydeberg equation, which writes 1 over lambda is equal to the Rydeberg constant times 1 over n1 minus 1 over n2. So notice how this equation is very similar to the equation derived using the Bohr model or the more recent Schrödinger model. So it's always good when your theoretical model matches the empirically derived model. Now, one thing I'd like you to really appreciate is that both of the equations derived either empirically or from the Bohr model are identical. They will give you the same result. Now, one little stipulation, one little unfortunate stipulation in these equations is that all of these equations can only be used for one electron atom. So this is hydrogen primarily. And this critical stipulation really leads into our next discussion, which we'll have later on in this chapter, which is how do we describe and how do we model the energy and reactivity for multi-electron atoms? It's non-trivial, non-trivial. Okay, so here's a nice picture that helps us relate our emission spectra, the color and wavelength of light observed, to the energy levels for each excited and ground state of hydrogen. So depending on the exact transition, a different wavelength of light is observed. Now, we can only see a relatively small number of wavelengths in the visible range, but there have been extensive studies into the ultraviolet and infrared emission spectra from hydrogen in order to create a full empirical model for the emission spectra of hydrogen. Okay. So let's put this into practice. So we're asked to find what is the wavelength in nanometers of light observed from the transition from n equals 4 to n equals 2. So we know that E photon, which is equal to hc over lambda, is equal to negative delta E atom. And that's equal to negative 2.18 times 10 to the negative 19th joules. Let me just check my equation to make sure I'm using the right constant. 2.18 times 10 to the negative 18th. Let me fix that. Okay. Times 1 over n final squared minus 1 over n initial squared. So we know that n final is equal to 2, n initial is equal to 4. So punching this into our calculator, delta E atom, negative delta E atom, which is equal to E photon, is equal to 2.18 times 10 to the negative 18th times 1/2 minus 1/4. Okay, so let's punch that into our calculator. So we have 1/2 minus 1/4 times 2.18. That gives us 5.45 times 10 to the negative 19th. Okay. Now we know that hc over lambda is equal to negative delta E atom. Ergo, lambda is equal to hc over negative delta E atom, which is equal to 6.626 times 10 to the negative 34th joule seconds. Ah, yes. Let's adjust that. My calculator didn't punch that in properly, so let's set that up. So we have 1 over 4 minus 1 over 16. Times 2.18. That gives us 4.09 times 10 to the negative 19th joules. Okay, perfect. And now we plug in our change in energy into our expression for the wavelength. So we have 3 times 10 to the 8th meters per second times 6.626 times 10 to the negative 34th joule seconds times 4.09 times 10 to the negative 19th joules. And that gives us a wavelength of 4.76 times 10, so we have 34. 4.76 times 10 to the 7th, negative 7th meters, which is equivalent to 476 nanometers. So punching this into looking at and comparing this predicted value to our observed transition from n equals 4 to n equals 2, we get a value of about 486 nanometers. So let's try punching this into our calculator one more time. And if we minimize and we do not round throughout, let's see what we get in our calculator. So we have 1, so I'm just punching this in my calculator one more time just to check for any calculator errors. So if you minimize rounding and you use the full value that you get out from this top expression, which is 4.0875 times 10 to the negative 19th, if we punch this into our calculator, that gives us a value of 4.86 times 10 to the negative 7th meters, or 486 nanometers. Now, this is really important, especially in this chapter, that when you perform your calculations, as we've seen in this example, you'd want to round only at the end of your calculations. So make sure to carry your whole numbers through, and that will give you the most accurate final response. And as we can see, if we do not round throughout our calculations, we end up with a number that very closely and almost exactly matches the observed emission wavelength for hydrogen. Does this example make sense to everyone? Does everyone understand the process that we need to follow in order to calculate the wavelength for a given transition? Can I get some responses in the chat? These are very common calculations that you'd have to do in order to, these are common calculations associated with this chapter, and we'll be elaborating on these calculations in order to, for example, as we see in this next example, to predict not only just the wavelength, but let's try now to predict the frequency of a transition. So what I want everyone to do is to work on this next example, and we'll spend about 3 to 4 minutes trying to calculate the frequency for the transition of hydrogen from n equals 3 to n equals 4. So we'll spend about 3 to 4 minutes on this next example, and then we'll come together as a group to discuss momentarily. So let's spend about 3 to 4 minutes predicting the frequency for the transition of hydrogen from n equals 3 to n equals 2. And then we'll discuss this example in about 3 to 4 minutes. Allow me one moment just to reset OneNote, as I'm noticing a little bit of delay. Okay, so let's work through this example and let's calculate the frequency for the transition of hydrogen from n equals 3 to n equals 2. And I would double check your delta E calculation. Just make sure that you square your N values in this equation. And we'll discuss this example in about another 2 to 3 minutes. Yep, and the response I see in the chat for the calculation proposed for this problem is exactly right. Let's keep working through this example, and I'd like to see a few more submissions for the frequency for the light emitted from this transition. Once we have a few more responses in the chat, then we'll be able to discuss. So you don't actually have to use HC over lambda. There's another, we can also write the energy associated with light in terms of just frequency directly. And that'll save you a few steps in the calculation. And we'll discuss this example in another minute to a minute and a half. And we'll discuss this example in another minute. Okay, so let's discuss this example. So first and foremost, E photon is equal to negative delta E atom, which is equal to positive 2.18 times 10 to the negative 18th joules times 1 over n final squared minus 1 over n initial squared. So that gives us a negative delta E atom value of 2.18 times 10 to the negative 18th joules times 1 over 2 squared minus 1 over 3 squared. Okay, so punching this into our calculator. That gives us 3.02777 8 times 10 to the negative 19th joules. We're retaining as many digits as possible, so that way we minimize rounding errors. So we know that E photon, which is equal to negative delta E atom, is equal to HV, which is equal to 3.027778 times 10 to the negative 19th joules. So we know that the frequency is equal to the change in energy of our atom over Planck's constant. That gives us 3.027778 times 10 to the negative 19th joules over 6.626 times 10 to the negative 34th joules second. So punching this into our calculator, that in turn gives us 4.57 times 10 to the negative 14th second inverse. Does this example make sense to everyone so far? Any questions on this example? So operationally, these calculations are not too bad. They just require you to be very meticulous with the amount of digits that you retain. Let's look at another example. In this case, we're asked to predict the wavelength for the transition of hydrogen from n equals 3 to n equals 2. So let's follow up on our earlier example, and I'd like you now to work on this following example for about another 2 to 3 minutes. And we'll discuss this example momentarily. And we'll discuss this example in about another 2 minutes. And keep in mind, we already calculated the frequency, so we can convert the frequency into the wavelength quite easily. I would recommend using the equation that directly relates the frequency and wavelength using the speed of light. The equation that we used all the way at the beginning of this chapter. That would probably make things a little bit easier, although your method is perfectly fine. Your method would work for sure. Yep, you're welcome to use either method. Both will work fine. And we'll discuss this example in another minute to a minute and a half. Yep. Okay, so let's discuss this example. So we know that the wavelength is equal to the speed of light over the frequency. So we know we have our speed of light, which is 2.998 times 10 to the 8 meters per second. And our frequency in this case was 4.57 times 10 to the negative 14th second inverse, or 1 over seconds. So punching this into our calculator, oh, this should be positive 14th. That in turn gives us a wavelength of 6.56 times 10 to the negative 7th meters, which is equal to 656 nanometers. Any questions on this example? Any questions on this example? If not, let's keep going and let's look at a little bit more of a tricky example where we're asked to predict the transition that results in a 434 nanometer. Just because in the earlier example, we have in our calculator, when I set it up, we have a negative power of 10 divided by a larger negative power of 10, which gives us a positive power of 10. Does that make sense? Perfect, perfect. So let's move on to this example where we calculate and we predict the transition that results in a 434 nanometer wavelength line for hydrogen. So we know the wavelength. So our first step is to calculate the energy of the transition. In this case, the energy is equal to hc over lambda, which is equal to 6.626 times 10 to the negative 34th joule second times 2.998 times 10 to the 8th meter per second over 434 nanometers. As always, make sure to convert nanometers to meters. We have 10 to the negative 9th nanometer per meter. That in turn gives us the following energy. So we have 6.626 times 2.998 over 434. That in turn gives us 4.577131 times 10 just punching in my calculator one more time, times 10 to the negative 15th joules. Okay, now there's a nice trick. The visible range occurs from about 200 nanometer to 700 nanometer. Yeah, sorry, that should be meter per nanometer. So the nanometers cancel. Yep, good catch. So the visible range is from 200 nanometer to 700 nanometer. And we know that the visible range, our n final, or our final quantum number value, is going to be 2. So if we know that E photon is equal to negative delta E atom, that would be equal to positive 2.18 times 10 to the negative 19th joules times 1 over n final squared, which is 2, minus 1 over n initial squared. So what we can do now is that if our E photon is 4.577131 times 10 to the negative 15th joules, and that's equal to 2.18 times 10 to the negative 19th joules times 1 over 4 minus 1 over n initial squared. All we have to do now is rearrange this equation. And that in turn gives us 1 over 4 minus 1 over n initial squared is equal to 2.0996 times 10 Let me just check the magnitude of my first response just to make sure everything lines up. Okay, everything looks good from a magnitude perspective. Okay, everything looks good. The n final is equal to 2 is based on the fact that the visible range will always have an n final value of 2. That's a nice little trick to remember as it makes these problems substantially easier. Okay, so now that we have this set up, I'm just going to check the magnitude of this first calculation again, just to make sure there are no errors. This should be 4.577 times 10 to the negative 19th joules. Perfect. Now let's punch this into our calculator and let's move this term to the left-hand side. So we have 4.577131 times 10 to the negative 19th joules over 2.18 times 10 to the negative 19th joules. So punching this into our calculator, let's punch this next calculation string into our calculator. And what we're trying to do is we're trying to solve for our n initial. So let's get this entered into our calculator. And let's really make sure that we're minimizing rounding errors. So I'm just punching this into my calculator. Okay, so punching this into our calculator, we end up with, oh, this should be 18. That's why. Okay, punching this into our calculator, we end up with 0.20996. Now what we're going to do is we're going to solve for n initial. So we're going to solve for n initial. So we get n initial so negative 1 over n initial squared is going to be equal to 0.2099, because if we take 4.57 times 10 to the negative 19th over 2.18 times 10 to the negative 18th, and this 10 to the negative 18th came from our equation to describe the energy and the change in energy of our atom, which is found here. So that's where the 2 times 10 to the negative 18th came from. It's part of our equation to describe the change in energy of our atom as it undergoes a transition. Okay, so we have 0.2099 minus 1/4. That in turn gives us 1 over n initial squared is equal to 0.04003, and that in turn gives us n initial is equal to the square root of 1 over 0.04003. And that in turn gives us an n initial value of 5. So this is the n equals 5 to 2 transition. So in summary, to solve these problems, first you calculate the energy of the transition. Then, since it's in the visible range, you know that n final is equal to 2. And then we substitute in and we solve for n initial. And n initial should always give us a whole number. I know it takes a few steps, but does this problem and does solving these types of problems where you're asked to predict the exact transition that generates a wavelength, does this make sense to everyone? Is everyone comfortable with this example? Any questions on this example? If not, let's now introduce some critical ideas in order to understand the quantum model of the atom. And it starts with this idea of quantization. So what does quantized mean? Well, energy is quantized if only certain discrete values are allowed. Just likewise, the presence of discrete wavelengths makes atomic emission quantized. So when we say quantized, what we mean is that the energy wavelength or another property, rather than having a continuous range of energy values or allowed wavelengths, only discrete energies, discrete values, discrete increments of energy are allowed. So think of it like a series of stairs or a series of steps that you move up and down rather than a continuous ramp. So for example, in equations, so for example, the energy associated with a photon, each photon has a discrete energy based on the frequency of light. So the energy of a photon is always going to be a common multiple of h, which is Planck's constant. So we can think of the energy of a photon as divided into discrete steps of h, where each time we increase our frequency, we're moving up a step in these different quantized photon energies. Likewise, if we think about the energy of an electron, the energy of an electron is divided into discrete energies based on n, which is our principal quantum number. So this idea of quantization is this idea that only discrete energies, discrete wavelengths are allowed. Okay, so continuing on, let's talk next about where does the Bohr model fail? Well, first and most obvious, as we pointed out, the Bohr model is not able to explain the spectra of atoms with more than one electron. Further, the Bohr model does not explain what's known as the collapsing atom paradox. Well, quite simply, in the collapsing atom paradox, as an electron, if it's supposedly orbiting the nucleus, as the electron rotates and orbits the nucleus, the electron would theoretically release energy. And as the electron loses energy, you would expect it to orbit closer and closer to the nucleus until eventually the atom collapses. However, we know for a fact that the electron does not just collapse into the nucleus, and the Bohr model can't fully explain why that occurs. As a teaser to what we're going to discuss later on in this chapter, the quantum mechanical model addresses this issue by noting that only certain electron energies are allowed. The electron is constrained in terms of what energy and what position relative to the nucleus it can occupy. Okay, so we've established that the Bohr model has some issues. Let's talk next about how we can reinterpret and think about electrons from another perspective in order to begin to model electrons more accurately. So to start off, we're going to have to introduce this idea of interference. So light, for example, is a classic wave, exhibits interference. Now there are two types of interference, known as constructive interference, where waves that are in phase add together to create a wave of greater amplitude. So we have an additive effect because the waves are in phase. Likewise, destructive interference is where we have waves that are out of phase, create waves of lower amplitude. They cancel out. So you have regions of opposite amplitude overlapping, and they add together and they cancel out. That's known as destructive interference. Now, if we project light through a series of slits, we observe a characteristic interference pattern, where light regions are regions of constructive interference, while dark regions are regions of destructive interference. So the key takeaway from this is that waves exhibit interference patterns when passed through a double slit diffraction grating. So waves can interact and their amplitudes can add together, and you would see these interference patterns of constructive and destructive interference. Now, what does that have to do with electrons, you may ask? Well, if we think about wave versus particle behavior, when a wave is passed through a slit, the wave will diffract and project out through the slit. If you have a particle will either pass through the slit or it won't. There's no diffraction behavior. Now, we know that light exhibits both wave and particle properties. We can think of light as both a light wave as well as a photon. Okay. But what about electrons? Well, if we try to perform a classic double slit experiment using an electron beam, what we can immediately see looking at our screen is that electrons also exhibit interference patterns, which is a characteristic wave property when they're passed through a double slit diffraction grating. Now, this is quite a shocking experiment when you think about it, because we typically think of electrons as particles rather than waves. Now, the key thing that we can take away from this experiment is that subatomic particles, such as the electrons that we're so interested in, can exhibit wave-like properties. Okay. Now, de Broglie proposed and sort of began to link this idea of particle behavior and the wave behavior of matter by proposing that electrons behave as standing waves with nodes of zero density about the nucleus. Okay, so what does that mean? So suppose that we have our nucleus, and suppose we have a distance that we'll call r. At that distance surrounding the nucleus, we have a general area that our electron is likely to be, and that electron can be modeled rather than as a particle. We can instead model the electron as a wave, more specifically a standing wave. So rather than describing and thinking about electrons solely as particles, we're going to begin to describe electrons as waves and standing waves. And we're going to use this wave-like description of electrons to begin to describe the position and energy of an electron. That's our goal in this entire chapter. So de Broglie's equation provides a link between the wave and particle models by providing a relationship between the wavelength, which is a wave property fundamentally, let me one moment just to reset OneNote. So it provides a relationship between the wave property and the particle properties of matter. So the wavelength is equal to Planck's constant over the mass of the particle times the velocity. And as we can see from this equation, only very small particles have appreciable de Broglie wavelengths. So let's look at an example and let's show why large objects don't exhibit appreciable wave-like properties. Obviously, if you have like a beanbag or a ping pong ball, a very large object, and we throw it at a double slit diffraction grating, we're not going to see a diffraction pattern on a macro scale for large objects. And that's because large objects do not really exhibit appreciable wave-like behavior. So for example, if we're calculating the wavelength of a ping pong ball, so we take Planck's constant over the mass times the velocity. For a ping pong ball, we see that the wavelength is equal to, so joules were equal to kilogram meter per second squares times seconds. So we have 6.2 grams. We know in a kilogram there are 10 to the third gram. We have 15.6 meter per second. So punching this into our calculator, we can see just by order of magnitude that a large object such as a ping pong ball would not have an appreciable wavelength. This has a wavelength value of 6.9 times 10 to the negative 33rd meters. So what I want you to take away from this idea is that microscale subatomic particles, such as electrons, can exhibit wave behavior. And we're going to use this model of electrons as waves rather than particles to begin to describe electron energy and the relative location of an electron. Okay, so that's it for this first lecture half. Are there any questions that I can address?